Question 9 says, the diagram shows how aluminium is extracted from its ore by electrolysis of molten aluminium oxide. It is carried out at high temperature with carbon electrodes. So this is obviously a C6 type context, but electrolysis is a C3 bit of knowledge. So it says, complete the balanced symbol equation for the decomposition of aluminium oxide by electrolysis. So C3 balancing equations. We can see that we've got 2 lots of the aluminium oxide, and we've got those numbers there. So I've got 4 lots of aluminium, so I can put a 4 in front of my Al, and I've got 6 lots of oxygen, and so I need to do 6 divided by 2 equals 3, and that can go in this gap here to make it balanced. Part 2 says, during electrolysis, reactions take place at the positive and negative electrodes. Complete the table to explain the reactions at each electrode. Use the diagram and the symbol equation to help you. So we've got our positive electrodes, our negative electrodes, and we've got these ions that they've shown us. We've got Al3+ ions and O2- ions. So I'll write those down here. These are the ions that we are dealing with. Now we know that opposite charges attract. So at the positive electrode, I'm going to attract the negative ions. So that's going to be O2-. And at the negative electrode, I'm going to attract the positive ions. So that's going to be the Al3+. Now, when I get there, am I going to lose or gain electrons? Well, my O2- has got to turn into oxygen. And it's currently negative, and it's got to end up neutral. So it's got to go back to being a normal element, which means it's got to give up or lose. So I write loss in here for the electrons, whereas my Al3+ has got to turn back into aluminium. And so it's gone from being positive to being neutral, so it must have gained electrons. Okay, and that makes sense as well, because it's going to pick them up from the negative electrode, whereas the O2- ions are going to give the electrons to the positive electrode. Okay, part B. For this one, we're just going to make some adjustments based on what our exact specification says. So I want you to cross out this, and I want you to cross out where it says oxygen and write in chlorine, and again here write in chlorine. Okay, so now we're going to do the question as though it's the kind of question that we might get. So it says, when salts are dissolved in water, the solution contains H+ and OH- ions from the water, as well as the ions from the salt. The products formed depend on the tendency of the ions to lose or gain electrons. And then we've got the table. Jamila does an experiment to electrolyze an aqueous solution of sodium chloride. She identifies the products as chlorine and hydrogen. She uses this apparatus. Describe how Jamila should use the apparatus to electrolyze an aqueous solution of sodium chloride and explain why chlorine and hydrogen are formed. So when we've got anything about using apparatus and describing how to use it, we should be thinking labeled diagram is the best way to go. So we can set up our apparatus with our beaker. So we can label this. And in our beaker, we are going to have our solution, so our electrolyte, which in this case is aqueous solution of sodium chloride. So aqueous sodium chloride. And we can have our electrodes connected to our battery. Now I've made it so that the left-hand side of my cell or my battery is the positive one, and that's the negative one because it's the shorter side. I can then remember this, my positive anode, negative is cathode. So these electrodes are my carbon rods, but this one is going to be the anode. And this is also a carbon rod, but it's going to be my cathode. Okay, so now I've done my labeled diagram, which explains or describes how I should set up the apparatus. Now I can do my explanation of the products. So we should know that with the positive electrode, so at the anode, Cl minus ions are present. And we know that if we've got an element that's in group 7, present in its ion form, so chloride is from chlorine, which is in group 7, then we're going to make chlorine at the anode. So we can say Cl minus ions are present, Cl is in group 7, so chlorine is formed, and the other one at the cathode we've got to compare the ions from sodium and hydrogen. So hydrogen is less reactive than sodium. So hydrogen gas is formed. Okay. If you're unsure where I got the sodium and the chloride from, we are using aqueous sodium chloride. Sodium is Na, forms Na plus ions because it's in group 1, so it loses 1 electron. Cl is in group 7, so it gains 1 electron. So my ions that I've got present from the sodium chloride are Na plus and Cl minus, and then the ions that I've got from the water are H plus and OH minus, and we've just got to think, out of these two, which one is going to be deposited, and out of those two, which one is going to be deposited at each of the electrodes. Okay, question 10. A company called Healthy Food make food colorings. The diagram shows the label from one of their food colorings. A representative for Healthy Food says the food coloring is pure. A scientist says that it is not pure. Explain the different meanings of the word pure used by the Healthy Food representative and the scientist. So, the Healthy Food representative, if we have a look at what the description is, we can see that all the ingredients are natural and tested. So when we talk about stuff being pure in a kind of everyday sense, saying something's natural means that it hasn't had anything added to it because it's derived from nature. So basically, they're just saying that it is natural. But when we're talking about from the scientist's perspective, we actually mean that there is only one substance present. Only one type of substance present. That could be one type of compound or one type of element, but it's got to be just one type. So I could have pure water, that's a compound, or I could have pure carbon, that's an element. The table shows the melting points of some substances, which two substances are chemically pure. Well, we know that if you have a pure substance, so pure substances will melt at a fixed temperature. Therefore, A and D, because they don't have a range, are the pure ones. The other thing we know is that impurities lower the melting point. Now, we didn't have enough information here to be able to tell on the basis of what the actual values are. But if I did have information about the melting point of a pure substance, and then I was asked to work out which of the samples I'd been given was most pure, I would never go for a sample that had a melting point above that of my substance, because if it's higher, then that means that it's just a different substance present. So it can't be whatever one they're asking about. C part 1 says, the dyes in the food colouring can be separated using paper chromatography. The diagram shows the apparatus used to separate the dyes and the chromatogram that is produced. Draw lines to connect each letter with its correct label. So we should know that the solvent front is how far the solvent reaches. So A is the solvent front. There is a typo there. Can you please write in the letter C? B is pointing at the, oh, I've just seen that there's two typos. That's not very helpful. B is pointing at the actual filter paper itself. That is going to be our stationary phase. So let's make a correction in there and write in stationary phase. And C is the solvent that I'm using, which is also known as the mobile phase, because it's the one that moves through the stationary phase or the paper. Part 2, which property causes the dyes in the food colouring to separate? It's nothing to do with their boiling points. It's nothing to do with what the colours are. It's nothing to do with the melting points. It's to do with the different distribution between the phases. In OCRA, we might say how soluble the dye is in the mobile phase. So think about if you've got some felt tip pen and a biro, and you've drawn in felt tip pen and biro on the same piece of paper, and then you've dunked the paper in water, you notice that the felt tip pen spreads. That's because the dyes in felt tip pen are soluble in water, but the biro won't spread at all because the ink in biro is not water soluble. And part D says the chromatogram can be used to find the RF values for the dyes. Measure the distance moved by dye 1, so make sure you do the correct one, and by the solvent, and use a ruler, and then calculate the RF value of dye 1. So obviously we're going to have different values, especially because you've got this on a compressed piece of paper compared to the original size of the exam. But we would use our ruler, we find dye 1, and we measure this distance here. And to measure the distance traveled by the solvent, I'm going to do that in pink, we measure this distance here. So between the baseline and the solvent front. And then if I do that, I should have got something like 2.4 for the distance traveled by the dye, and about 5 for the distance traveled by the solvent, so 5.0. Now, it doesn't matter what value you get, so you can measure your own value and then put it into your calculator, and you should still get the same RF value at the end. So I do 2.4 divided by 5.0, which is equal to 0.48, and that's what I can put here. And a clue is the RF value should always be between 0 and 1. So if you ever get an RF value that's more than 1, you've probably done your fraction the wrong way round, and so you need to just swap your numbers in your fraction.